we will now see a program to compute 10 plus 13. And this is a very simple program, clearly, and an optimizing compiler would make it even simpler by just storing 23 somewhere. But that's not the purpose now, but instead to see what such a program can look like. So we have, or we need to use two add instructions to put 10 and then 13 into a register. So we will use 10 for this register, and 13 will be put in register 2. So the operands here, they are sometimes they mean a register number, and sometimes they mean a constant. And which one is which depends on which instruction it is. So this sub instruction, it subtracts register 0 from register 0, which clearly becomes 0, and puts that in register 0. So what it does is to clear register 0. And then we can add register 0 and 10 and get the constant 10 in register 1. So that's what happens here. And the same for 13 and register 2. And then what we do is to add them. And then we halt the computer. Okay, so let's look at the more complicated program. We will look at the machine.c in a short while. So let's instead compute the sum from 1 to 100. And what we can do then is to say that we have a variable sum, and then we use register 1 for that variable, and we start by setting this variable to 0 by subtracting in the same way as we did before. And I is in R2, and we set it to 0 as well. Okay, then the upper loop bound we put in register 3, and we do that like this. And then what we want to do is to check if R2, I mean if we should end the loop. And if we should, then I mean if we are, I has become 101. And then we should branch to instruction 8, which is to halt the machine again. Okay, so what we do here is to save a Boolean value that R2 is greater than R3 in register 4. Some machines have special compare instructions which set a special register, but in this and in some others, such as MIPS, which is another, this one comes from Stanford. Well, it doesn't matter now, but it's also a product. Okay, and they use a normal register to save the Boolean value of a comparison. So SGT means set greater than. Okay, and R4 will be either 0 or 1, depending on whether this was true or false. And then we do branch if true, using this register. I mean the same that we used there. The first operand is not used, but it has to be there for this simple program. I mean for the machine.c when it reads this file. And then the constant here is the destination address. Okay? And if we didn't branch, then we increment the sum. And then we increment I, and then we branch unconditionally, or branch always, to address 0. So we start up here again. And then we continue. Okay, we will look at the factorial also, but let's look at the C code for this simulator. So it looks like this. It's in the Tresorit directory, and this is the documentation. All the opcodes, they have a certain number, and here is what they do. You don't need to use this for a lab or anything, but it's really the simplest way to understand what the CPU does. Okay, so we have these opcodes, and which opcode is in an instruction determines what the CPU should do. Okay, so there are branch true, branch false, branch always, store, that's write to memory, and what does it write? It writes a register called RT, target register, and the sum, the address that it should write to is one register plus a constant, and it can read and it can call. Now we come to something interesting, which you may not be aware of that it's needed. But when we jump to a function, we must be able to do return, clearly. And we should return at the instruction after the call instruction. So what this hardware does is to add the program counter and save it in register R31. And then it sets the program counter to a constant. And that constant is the address of the function that we want to go to. Okay, and then there is a jump to set the PC to a certain register value. We can multiply. We can set equal with a constant. This I is usually called immediate. An operator, which is a constant encoded in the instruction, is called immediate operand. Okay, and then that was the halt. Okay, some extra here to initialize an array of strings. So we use, this is C99, and well, each of these constants is used to decide at which position in this array. The array is an array of car pointers, so we can save strings there. Okay, that's for printing out what happens. So this is the complete CPU. As we can see, it's extremely trivial. Okay, so it's a struct, and it has this program counter, and it has an array of registers. Then there are some functions that we will not look at because it uses operators. They use operators that we haven't introduced yet. But for instance, you remember that the opcode was in power. It was the 6 leftmost bits. So what this does is to shift the instruction 26 positions to the right, and then only the opcode remains. So that's a way to get the opcode. Okay, and then there are different fields of the instruction that we should extract. Okay, that's just an arrow. And here we read the assembler program, which we can ignore. And in addition to the CPU, we also have memory. And this memory, it is 1024 ints, and this was 32 registers in the CPU. Okay, then we have some things which we can ignore for the moment, and we start with reading the program, and now comes the execution of a CPU. So we set the program counter to 0, and then this is what happens when a CPU executes a program. It uses the program counter as an index to this memory array, which was read, I mean the program was loaded to the memory before, above this, and then we get an instruction, and now we want to decode the instruction. That means getting the bits corresponding to the opcode, to a source register, to a constant, and to a destination register. Okay, now you probably react that it's not certain that we use a constant. That's true, but what we do is to, okay, I will draw it like this. Say we have, oops, this doesn't work because it's not the PDF file. Never mind. Okay, so what I will explain that in a different place. We can do it here. Okay, so say we have an instruction, and we have this ADDI. Okay, then there is an opcode and a target register and a source register, and then a number. So say this number 100. Okay, so it's there. And then what we did was to extract this number. So we get 100 into the variable called constant here. Okay, and we also got source reg1. Source reg1, that's this one. Say it may have been well, R1 for instance, and we got the destination register, namely this one, destreg. So that's the destreg. No, not there, but there. Okay. Say now, so now we have extracted the constant and the register number and the destination register number, and here is the opcode. Okay, say now that we have this instruction instead, namely that we add two registers. Okay, opcode, and then we have destination register, first source register, and then instead of using the constant, we use only this part. So this is second source register. Say this is that we want to do R3 should be set to R1 plus R2. Okay, then 3 will be written there, 1 will be written there, and 2 will be written there. Okay, but when we decoded the instruction, we took all these bits. Just in case this was a constant. But if we determine that we should use the register contents, I mean the value of R2, then we need to use this 2 as an index to the register array, but we should clearly only use the bits that correspond to this. Okay, so how do we do that? So now we will see. We should check, we should fetch two register values. And the first is, there is no doubt what it should be done. It's just using this source reg1 as the index into the register array and get the value. Now, to get the second register source operand, what we do is to do something a little bit funny. We take the constant and then we say and, that's bitwise and the number of registers minus 1, and use that as the index. How come? Well, what we want to do is to extract these bits. Okay, let's magnify and say we have 16 bits here, and we want to get this part. Here we want to read 2. Okay, here may be anything. Here can be just some garbage, for instance. And what we did was to take the constant that we read and say here, we read the constant, that's all of this, interpreted as a constant. Okay, and then we use this constant and say and nreg -1. Okay, what does that mean? So we take this value and that bitwise and with nreg -1. Nreg, that's 32, and -1, that's 31, and 31, that's 5 bits. So, sorry, it's 5 ones. So 1, 2, 3, 4, 5. Okay, and the rest here will be zeros. Okay, so this is the way to extract. Maybe we should write this 2 as in binary instead. Okay, so it should be like this. Okay, so what will the register, the index to the register array be? Clearly this, if we do this bitwise, this will be gone and only these 2, the value 2 will be used. Okay, so in the end we get 2 in that base, and then we will write reg 2. Okay, and why did we want that? Well, we wanted the value of register 2. Okay, so that is how we can do that. Okay, now we still don't know that we actually want a register here, the value of the register, or that we want the constant. Why don't we know that? Well, we haven't checked which opcode it is yet. But depending on which opcode it is, we will either use the constant or source 2. So here is we can look at that at once actually. So when we add 2 registers, it's this one. Then we add, the first register value and the second register value, and save that in the destination, the result. Instead, if we have an add immediate, then we add register value, the first one, and then we add the constant to this and save it in the destination. So the opcode decides which operand it wants. The code that reads the opcode decides. And this happens to be C, but it could be in any hardware description language, such as VHDL or something else, and it looks pretty much the same. Well, it was quite a number of years that I used VHDL, but it's basically the same idea. Okay, so what else do? We say that we should increment the program counter, and we should write back the result to the register file. Okay, unless we change our mind later. So we do that, and then we can see different instructions. What they can do, they can subtract the constant, multiply, set greater than equal, for instance. Well, everything of this is just as expected. I am sure. Okay, now here we have something interesting. BT, branch if true. Okay, the first thing we do is to say that we should not write back any value to the register file. So we say write back is false. And then if the source value is non-zero, then we should branch. Okay, so what we do is to set the program counter to the constant and do not increment the program counter. We say that we shouldn't increment it. For branch false, it's the opposite. For branch always, well, there is no if, of course, so we just say that we should branch in that direction. Okay, a load instruction. We read from memory, then we use the content of the first register and the constant and read that from memory. And then we say that the destination should be this data that we read. If we want to store, then we get data from the register and then we write that to the memory. And we should not update any register, so we say write back is false. Okay. Call, then we make a function call. So what we do is that we should not increment the program counter, and what we should do is to the data that we should save in register 31 is the address of the next instruction, the address of the instruction that we want to return to. Okay. For instance, what does that mean? I think you know, but when this simulator calls this put string function, we clearly expect we will return to just here after that one has done its work. And that's the reason why we want to save the address of the next instruction somewhere, and we save it in register 31. Okay, and then we set the PC to that constant. To the constant in the instruction. Jump, that's when we want to jump to actually when we want to do a return, but in general we can use this to jump to the value of a register. Okay, halt is, well, that's just something to stop this loop. The proceed becomes false. Okay, and if there was no such instruction, then we complain. Okay, so if we should write back the result, we update the register file or register array. If we should increment the program counter, then we do that. And here are some debug outputs, dumping all the instructions and dumping all of memory, and then that's commented out using this method, and so everything between this if 0 and the end if, it's skipped. Okay, and then after each instruction we print the value of each register. Okay, so let's see what happens. Okay, we say GCC machine. Okay, and then we run this program. Well, which one should we take? We can take this one. It should produce 23 somewhere. Okay, so, well, it's not very strange. We start with setting things to 0, then 10 over there, and 13 there, and then 23 there, and then we halt. Okay, and let's do the sum instead. We will not look at everything, but well, we add and jump unless we are finished. Well, are we finished? Then we jump to instruction at address 8, and here is the result as expected. Okay, So I think you have got an idea of what the CPU does. What we will do next is to look at a recursive program to see more tasks that the software must undertake in order to make this program work with this hardware.